In this video, I will summarize my storyline experience that revolves around the question, why do some things get colder or hotter when they react? But first, what is a storyline? Well, let me enlighten you. A storyline is a coherent sequence of lessons in which each step is driven by students' questions that arise from their interactions with phenomena. In my high school chemistry lab, students carried out several simple physical and chemical reactions. They asked questions based on their observations, and they created models of the observed phenomena. But what really drives home the concepts of matter and energy are the subsequent students' revisions to their original models and their revisions to the related questions. So let's go through the first 7 lessons that make up this storyline. The description below contains the link to my Google Drive folder containing all the lessons and my generated keys to these lessons. I should emphasize that I adapted these lessons from the Next Generation Science storylines and the inquiryHub chemistry curriculum. Let's get started with lesson number 1. What happens when these substances are mixed together? This is the handout, but let's dive right into the lesson. Okay? So students are mixing 2 solid chemicals, barium hydroxide and ammonium chloride. And upon stirring, they notice a beaker can be lifted together with a wooden block because water in between the two was solid frozen. That basically precipitates some questions. The first question one might think of is the following. If we mix 2 chemicals, will a chemical reaction always occur? And why might this be viewed as a chemical reaction? Again, they saw the temperature drop, and they also noticed a very pungent odor coming away from the beaker. So the second reaction that the students are doing is mixing pink lemonade powder, not necessarily shown in this GIF animation, but we'll make it more funky, and baking soda. So when you mix these two, very similar to mixing simple vinegar and baking soda, is that a gas is released. And again, the temperature is dropping. Profound. We've just done 2 reactions, mixing 2 chemicals. Will a chemical reaction always occur? Maybe, but based on those 2 observations, students might think, sure. Some other questions that may come into their mind. When we mix chemicals, what evidence suggests that there is a chemical reaction occurring? So we've observed that temp drop, and we've observed a gas release, whether that was a pungent gas or fizzing in the beaker. So 2 different observations that have led students to think there's a chemical reaction happening. But then the question might come, if we mix 2 chemicals, will the temperature always decrease? And based on those 2 reactions, it sure did. Another question as part of our discussion board. How can we best model a reaction that results in such a temperature decrease? Okay, let's think. So what I'm showing you here is a very simple model. We've got 2 different chemicals. They are considered our reactants. We're putting the 2 together in a beaker. We now are turning them into possibly new products and a concomitant gas release. All right, so maybe that means old bonds are broken, new bonds are formed. So this is considered our model in progress. Let's keep going. So back to our discussion board. So maybe we've now answered that model question. We might come back to it later. And here we are on our next question. If we mix 1 chemical, not 2, but just 1, with water, by the way, water is also chemical, but you know what I mean, will the temperature decrease? Let's check it out. So now we're on our second lesson, titled, do only chemical reactions get colder? Handout? Let's keep going. So, in this particular video, I'm showing you how adding potassium chloride to a beaker with some deionized water is resulting in a temperature drop. I know, we want to speed this up a little bit, but it's happening, trust me. Let's get that stir bar going, and there we go. Temperature is dropping. So, okay, solvation of KCl, what is happening during this reaction? Besides the temperature change, the temperature drop, is anything else going on? I don't see a gas release. So that brings us to another question on our discussion board. If we dissolve a substance in water, is this considered a physical or a chemical change? And the YouTube image reminds me that I've already done a video on that. So if you want to see this in great detail, go to that video. But briefly, how to evaluate whether solvation is a physical process? Well, you can simply go through the steps. Measure out your salt, measure out your water, dissolve the two, and then try to get the same amount of salt back. That's your first piece of evidence. The amount of KCl dissolved and retrieved after the solvation is roughly equal. What else could you do? Evidence 2. Well, your potassium chloride as a solid, if you do a flame test with it, it should give you pretty much the same color in a flame test when you use a sample of potassium chloride in solution. And it's about a pinkish orangey color, depending on how you view your colors. And then thirdly, you may promote your students to take some conductivity samples of the various steps in this solvation reaction. The control, just hooking up some alligator clips to the prongs on this conductivity meter, obviously should really show a bright red and bright green shining of the light bulbs. But the only other one that's really going to make it shine is the actual solution. So something did happen to the potassium chloride in solution. But in any case, for now, we can say solvation is a physical process. Okay, let's bring this back to our discussion board. Why does the temperature decrease when chemicals are mixed? And how can we best model a reaction that results in a temperature decrease? Let's think about that. So lesson 3 delves into exactly that question. Why is the thermal energy decreasing when KCl dissolves in water? So this lesson really focuses on making a revised model from the one that I showed you before. So to encourage a very detailed model, I actually show my students 2 GIF animations, as you can see here below. And that might lead them to something very fancy, possibly, and perhaps a bit complicated as the model that I drew here. So with some coaxing, with some lead-in questions, you might get your students to come up with a drawing of potassium chloride as a very organized crystal lattice and water molecules somewhat connected through hydrogen bonding. And they have a significant amount of kinetic energy as indicated by those red squiggly lines. So in essence, that kinetic energy indicated by the flame is going to result into a breaking of bonds. And those bonds being broken enables the potassium and chloride ions to reform new bonds, namely ion dipole forces, with the water molecules. As a result, again, the temperature drops, shown by the cold emoji. Okay, so how can we best model a reaction that results in a temperature decrease? Well, I just showed you a model. Is that the best one? So, lesson 4. What makes atoms stick together? lesson handout. Let's dive right into the lesson. Okay. All different kinds of GIF animations here. Don't get too overwhelmed, but it shows you different ways that students can come up with ways to model bonding, ways to model atoms sticking together, whether it's Lego pieces or paperclip pieces or duct tape, cement, the striking of a match held together here with an elastic piece, and then Velcro or simple glue, or what's that at the bottom there? Magnets or a nail and a hammer. So they quickly come up with the idea that maybe magnets are the best way to model atoms sticking together. So check out my key for some best hints why you can encourage your students to go with the magnet idea. Okay, so are magnets a good model for the connection between particles? Lesson handout, again, key below, we keep going. So this is a reminder to tell you that one of the earlier videos I did was showing you exactly this. Are magnets a good model for the connections between atoms? I think they are. So how did I model this with my students? Well, I used a ramp that I got from my earth science colleague. I used a pretty strong neodymium magnet taped underneath the ramp, and both a metallic and some non-metallic marbles to try and break the bond between the magnet and the metallic marble. Let's check it out. So what we're seeing here is a red non-metallic marble drop down from the ramp. I better hit the play button again so you could see it again. And there is a speedometer here that can actually measure the speed by which this is happening. And clearly that bond is broken, causing a drop in speed of the non-metallic marble, which after that original drop, post-collision, it's going to increase the speed again. But this is how the kinetic energy of the incoming non-metallic marble is changing as a result of the bond breaking. Isn't that cool? So that might lead students to come up with another profound question. Are all chemical bonds the same strength? Are all magnets the same strength? Let's find out. So, lesson 6, are all bonds the same? And this lesson, very recently, I also turned into a video where I have my students measure the temperature rise and drop of 7 different salts. Let's check it out. So this shows you the actual Google Sheets data chart, which displays the differences in temperature, whether it's a rise for sodium hydroxide and potassium hydroxide, or a drop considering the salts ammonium chloride, ammonium nitrate, potassium chloride, sodium nitrate, and maybe less so sodium chloride. So are all bonds the same? I don't think so. So, all right, so I've done some revisions here of the questions. Why does the temperature change, clearly not just a decrease, when chemicals are mixed? And how can we best model a reaction that results in a temperature change, although we'll get to that? And are all chemical bonds the same strength? Well, clearly, no. So that brings us to lesson 7, our last lesson in this particular video. That's not the end of the storyline, but it's where I think we should take a break. So lesson 7, going back to the first chemical reaction. Why did barium hydroxide and ammonium chloride absorb energy? Again, here's the lesson handout. Let's dive right into it. So my focus here is how to model now that particular reaction. So students in this particular lesson are playing with these colored atom cards, showing you nitrogen, hydrogen, chlorine, barium, oxygen. And I've now showing here how I would model these bonds. So in the, I don't know, is that teal? The teal color, you're seeing the ionic bonds. And the flames are actually showing you that it requires some kinetic energy to break these bonds. Okay, let's do that. Let's show that. So now these bonds are broken as part of our transition stage. So then what's going to happen? Well, we're going to see some reshuffling. So instead of ammonium hooking up with chloride and barium hooking up with hydroxide, let's mix it up a little bit. We'll make it more spicy, right? So ammonium's now going to hook up with hydroxide, barium with chloride, but notice that the teal bars are thinner. New ionic bonds that are probably weaker than the original bonds, as evidenced from these flames, because when bonds are formed, energy is released, but in this case less so because the temperature is getting lower. The reaction feels colder because the original bonds, the original ionic bonds, took more heat to break than is released during the formation of these new bonds. Profound, right? I'd say. This brings us back to our discussion board, and I've kept two questions there. Why does the temperature change when chemicals are mixed? And how can we best model a reaction that results in a temperature change? Changed from decrease. So, what should our students do? I'm going to encourage them to basically transfer those questions because, in my opinion, they are key questions based on this whole storyline and what they've done so far that should be transferred to Google Keep. And this is a reminder to share with you that I have a video on Google Keep that basically explains how I take notes and make notes with my students in my chemistry classes in Google Keep, using Google Keep, and how best to capture, organize, distill, and express these notes. So that brings me basically to the culmination of the first half of this storyline. Why do some things get colder or hotter when they react? I've shared with you 7 lessons, again, in the description below with the key. And stay tuned for the sequel to this, which I haven't even completed with my own chemistry students. The sequel to this storyline, why do some things get colder or hotter when they react? Thank you so much for watching and see you in the next video. Bedankt voor het kijken en tot ziens!